Hi everybody. In this video, we'll extend our understanding of inference procedures for proportions to scenarios involving two samples now. We'll take a look at a hypothesis test and a confidence interval. So here's our first example. A forest in Oregon has an infestation of spruce moths. In an effort to control the moth, one area has been regularly sprayed from airplanes. In this area, a random sample of 495 spruce trees showed that 81 had been killed by moths. Second nearby area receives no treatment. In this area, a random sample of 518 spruce trees showed that 92 had been killed by the moth. Do the data indicate that the spray is effective in reducing the proportion of trees killed by moths? So we'll have to look at here, but notice we do have two samples. We have one sample that was regularly sprayed by the airplanes. We have a sample size and a number of successes, that being the number of trees killed by moths. We have a second sample here of those that were not sprayed by the airplane. We have a sample size and a number of successes here. So naturally here we have two sample proportions to look at. First, we have the sample proportion of trees that were sprayed that were killed by moths. That's 1.1636. And the sample proportion of trees killed that were not sprayed, which is 0.1776. So there's a difference, but maybe not that big of a difference. But there's also going to be a third proportion lurking around here that we need to look at, and that's something called the pooled sample proportion. And what the pooled sample proportion is used for is, consider at the beginning of this problem, we don't know if one of the treatments works. So we're going to assume right now that treatments are equal, and we're going to take all of the samples and the successes and put them into one big pot. And we will assume this proportion until we are proven otherwise. That's called the pooled proportion, and here you see it in white. It's 0.1708. It's going to come into play in some of our calculations. So let's dive into our state plan to conclude. First of all, state the null and alternate. They're listed here. This time we have two population proportions to compare. The population proportion of trees sprayed versus the population proportion of trees not sprayed. And we do want to define what these stand for. P sub S is the proportion of all sprayed trees which would be killed by moths, versus PNS, which is the proportion of all not sprayed trees which would be killed by moths. And our alternate hypothesis says that the proportion for sprayed is less than the proportion of not sprayed. There is another way to write this as well. It's not a better way, it's just another alternate way you might see it. Some people algebraically like to just move that other parameter to the left side so that we're talking about 0 as a comparison. Again, not one is better, they're just different. Okay, plan. We're going to do a two sample z-test for difference between population proportions. Many of the same conditions here, but just adjusted a bit for the fact that we have two samples. First of all, the random condition, we have independent random samples, and it turns out that that plural really does matter here. Make sure you use plural here. Saying SRS's is also acceptable here. Independence, both samples come from large populations. We know our independence rule is the population has to be at least 10 times as large as the sample. You need to do this for both of the populations. And our normality condition, the expected number of successes and failures in both groups is greater than or equal to 10. We will compute this using the pooled proportion. Again, we are assuming that pooled proportion is the truth until we are proven otherwise. And here we have 495 times 0.1708, and we have to do it for both samples. So we have 4 computations to do, but they're all clearly greater than 10. All right, the do part. This will be the most technical piece of this. We're going to compute the test statistic and the p-value. And we do have a formula for the test statistic here. This is a z procedure. This looks pretty intimidating, but it's no different than the z-score we've seen before, where we have the difference between what was observed minus the null here, which is 0, over some standard error. Now, this standard error might look a little intimidating, but look what we're doing here. We're just taking the standard error from one sample, and we know that standard deviations don't add, so we square that to get the variance. We add the variances together, and then we square root the whole thing. So we have something kind of messy looking, but really should make some sort of sense. These formulas in a slightly different form are given to you in the AP Statistics formula sheet. So I've taken the time and plugged those all in. It is kind of a pain, and we'll talk about that in a minute. I have a z-statistic of negative 0.591, which we should already indicate is probably not going to be statistically significant, and it has a p-value of 0.2773. But this does bring up a big question. Do you really need to write this all out? So I'm going to give you somewhat of a half answer here. Let's do the do part again. So we love the formula. We should understand the formula. We should embrace the formula. But on the AP exam, you don't really need to write it out unless you're really brave. And if you're brave, please be correct. If it's wrong, we will find that and you'll probably get dinged for that. So at this point, it is totally okay to go to your calculator. Call this a two-prop z-test. You put in the number of successes and failures for both groups, and you should have the z statistic and the p-value. You may want to pause and make sure you can find this on your calculator now. And don't forget to include both of the p-hats would be nice, and a sketch of the normal distribution that you use here. Now we go to the conclusion. We're going to make both a statistical and a contextual conclusion. Look back in your alternate. What is it we're trying to prove? We're trying to prove that the spray reduces the incidence of deaths from moths. Since our p-value is greater than alpha, 0.05, we do need to say what significance level we're going to use. We fail to reject the null in favor of the alternate. And this means we cannot conclude that the proportion of all trees killed would be lower for trees sprayed versus those not sprayed. So just a couple new things here in the two sample test for proportions. Let's take a look at a confidence interval problem now. Oh, and be careful, don't use past tense, speak in future tense. Yes. We're trying to extend to all trees in the forest here. Okay, now let's go to the confidence interval. Here's our confidence interval example. At Community Hospital, the Burn Center is experimenting with a new plasma compress treatment. For those with minor burns, some patients were randomly assigned the plasma treatment. For the 316 patients who received the plasma treatment, we have 259 who had no visible scars after the treatment, and 419 patients were randomly assigned to no plasma compress, and there 94 had no visible scars. We want to estimate the difference of proportions of patients who had visible scars between the two treatments. We've got a couple little small differences here, but we do have two samples. Let's take a look at what we're trying to do here. We want to estimate the difference in proportion of scars for patients who receive a plasma treatment at community hospital. Something different about this one, we don't have two random samples. We have one hospital where patients were randomly assigned. So our goal here is to try to estimate a difference for all patients at this hospital. And we'll see what happens here in the plan as we go forward here. We'll construct a 95% confidence interval for the difference in population proportions. Here's the plan. We're going to do a two-sample z interval for the difference between population proportions. Now, random. We don't have two random samples. Instead, the subjects were randomly assigned to one of two treatments. These are not SRSs, so it really pays to pay attention how the data was collected and mimic that within what you write here. Okay? And there's only one population. This also does mean we'll be able to extend our findings to all patients at community hospital. Independent, we have independence between the samples, and one population has to have a population size of greater than 7,350. I got that 735 by adding up the two sample sizes to get one big sample that was taken from the hospital. So the population must have a large number of burn patients. And normality, the number of successes and failures in both groups is greater than or equal to 10. Keep in mind we're doing a confidence interval here. So in this case, we're using the actual number of successes and failures. We do not have a null hypothesis to go by. So all four of the numbers that were given to us are greater than or equal to 10. Okay, this is another nasty, but it's another formula that's somewhat reasonable. Here it is. Again, we're going to take the difference that was observed, plus or minus z star. And again, the standard error part is just adding up two variances and square rooting. And we will do this for each of the samples. It's no fun to type it all in. We do have our two sample proportions. P hat for the plasma treatment is 0.820. The p hat for no plasma is 0.224. Clearly a difference between the two. We want to assess how different these two things might be. Plug it all in. It's a lot to type in. This is our 95% confidence interval. And then we just rely on technology to give us a confidence interval of 0.5370 to 0.6536. We will use the two prop z interval in this case. Again, you may want to pause and familiarize yourself with how that command works. Now we're going to conclude. We want to generalize to all patients within the population, which is community hospital. So no past tense language. We want to estimate how much more effective one might be than the other. So we'll say we are 95% confident that there would be between a 73.7% and 65.4% difference in scars for patients who receive the plasma treatment for their burns at community hospital compared with those who don't receive such a treatment. Again, that interval is trying to capture the difference between the proportions of patients this versus this. There's a couple of ways you can say it. I'm kind of happy with that one there where it compares the plasma treatment to the non-plasma treatment. So that's all. Two sample intervals and hypothesis test. Not much different, but a couple more things to think about. And they're starting to get a little bit more nasty with the formulas.